The abstraction, the process. In this chapter, we discuss one of the most fundamental abstractions that the OS provides to users, the process. The definition of a process, informally, is quite simple. It is a running program, V plus 65, BH70. The program itself is a lifeless thing, it just sits there on the disk. A bunch of instructions and maybe some static data waiting to spring into action. It is the operating system that takes these bytes and gets them running, transforming the program into something useful. Turns out that one often wants to run more than one program at once. For example, consider your desktop or laptop where you might like to run a web browser, mail program, a game, a music player, and so forth. In fact, a typical system may be seemingly running tens or even hundreds of processes at the same time. Doing so makes the system easy to use, as one never need be concerned with whether there are CPUs available. One simply runs programs. Hence our challenge, the crux of the problem, how to provide the illusion of many CPUs. Although there are only a few physical CPUs available, how can the OS provide the illusion of a nearly endless supplies of said CPUs? The OS creates this illusion by virtualizing the CPU, by running one process and stopping it and running another, and so forth. The OS can promote the illusion that many virtual CPUs exist when in fact there is only one physical CPU, or a few. This basic technique, known as time sharing of the CPU, allows users to run as many concurrent processes as they would like. The potential cost is performance, as each will run more slowly if the CPUs must be shared. To implement virtualization of the CPU, and to implement it well, the OS will need both some low-level machinery and some high-level intelligence. We call the low-level machinery mechanisms. Mechanisms are low-level methods or protocols that implement a needed piece of functionality. For example, we'll learn later how to implement a context switch, which gives the OS the ability to stop running one program and start running another on a given CPU. This time-sharing mechanism is employed by all modern OSs. Tip: use time sharing and space sharing. Time sharing is a basic technique used by an OS to share a resource. By allowing the resource to be used for a little while by one entity, and then a little while by another, and so forth, the resource in question, e.g. the CPU or a network link, can be shared by many. The counterpart of time sharing is space sharing, where a resource is divided in space among those who wish to use it. For example, disk space is naturally a space shared resource. Once a block is assigned to a file, it is normally not assigned to another file until the user deletes the original file. On top of these mechanisms resides some of the intelligence in the OS in the form of policies. Policies are algorithms for making some kind of decision within the OS. For example, given a number of possible programs to run on a CPU, which program should the OS run? A scheduling policy in the OS will make this decision, likely using historical information, e.g., which program has run more of the last minute, workload knowledge, e.g., what types of programs are run, and performance metrics. Is the system optimizing for interactive performance or throughput to make its decision? 4.1 The abstraction process. The abstraction provided by the OS of a running program is something we will call a process. As we said above, a process is simply a running program. At any instant in time, we can summarize a process by taking an inventory of the different pieces of the system it accesses, or affects, during the course of its execution. To understand what constitutes a process, we thus have to understand its machine state, what a program can read or update when it is running. At any given time, what parts of the machine are important to the execution of this program. One obvious component of machine state that comprises this process is its memory. Instructions lie in memory. The data that the running program reads and writes sits in memory as well. Thus, the memory that the process can address, called its address space, is part of the process. Also part of the process machine state are registers. Many instructions explicitly read or update registers, and thus clearly they are important to the execution of the process. Note that there are some particularly special registers that form part of this machine state. For example, the program counter, PC, sometimes called the instruction pointer, or IP, tells us which instruction of the program will execute next. Similarly, a stack pointer and associated frame pointer are used to manage a stack of function parameters, local variables, and return addresses. Finally, programs often access persistent storage devices too. Such I/O information might include a list of the files the process currently has open. Tip: separate policy and mechanism. In many operating systems, a common design paradigm is to separate high-level policies from their low-level mechanisms, L plus 75. You can think of the mechanism as providing the answer to a how question about a system. For example, how does an operating system perform a context switch? The policy provides the answer to a which question. For example, which process should the operating system run right now? Separating the two allows one easily to change policies without having to rethink the mechanism, and thus is a form of modularity, a general software design principle. 4.2 Process API. Though we defer discussion of a real process API until a subsequent chapter, here we first give some idea of what must be included in any interface of an operating system. These APIs, in some form, are available in any modern operating system. Create. An operating system must include some method to create new processes. When you type a command into the shell or double-click on an application icon, the OS is invoked to create a new process to run the program you have indicated. Destroy. As there is an interface for process creation, systems also provide an interface to destroy processes forcefully. Of course, many processes will run and just exit by themselves when complete. When they don't, however, the user may wish to kill them, and thus an interface to halt a runaway process is quite useful. Wait. Sometimes it is useful to wait for a process to stop running. Thus, some kind of waiting interface is often provided, miscellaneous control. Other than killing or waiting for a process, there are sometimes other controls that are possible. For example, most operating systems provide some kind of method to suspend a process, stop it from running for a while, and then resume it, continue it running. Status. There are usually interfaces to get some status information about a process as well, such as how long it has run for or what state it is in. Figure 4.1 loading from program to process, which illustrates the CPU, memory, and disk working in tandem for processes. 4.3 Process creation, a little more detail. One mystery that we should unmask a bit is how programs are transformed into processes. Specifically, how does the OS get a program up and running? How does process creation actually work? The first thing that the OS must do to run a program is to load its code and any static data, e.g. initialized variables into memory, into the address space of the process. Programs initially reside on disk, or in some modern systems, flash-based SSDs, in some kind of executable format. Thus, the process of loading a program and static data into memory requires the OS to read those bytes from disk and place them in memory somewhere, as shown in figure 4.1. In early or simple operating systems, the loading process is done eagerly, i.e. all at once before running the program. Modern OSs perform the process lazily, i.e. by loading pieces of code or data only as they are needed during program execution. To truly understand how lazy loading of pieces of code and data works, you'll have to understand more about the machinery of paging and swapping. Topics we'll cover in the future when we discuss the virtualization of memory. For now, just remember that before running anything, the OS clearly must do some work to get the important program bits from disk into memory. Once the code and static data are loaded into memory, there are a few other things the OS needs to do before running the process. Some memory must be allocated for the program's runtime stack, or just stack. As you should likely already know, C programs use a stack for local variables, function parameters, and return addresses. The OS allocates the memory and gives it to the process. The OS will also likely initialize a stack with arguments. Specifically, it will fill in the parameters to the main function, i.e. argc and argv array. The OS may also allocate some memory for the program's heap. In C programs, the heap is used for explicitly requested dynamically allocated data. Programs request such space by calling malloc and free explicitly by calling free. The heap is needed for data structures such as linked lists, hash tables, trees, and other interesting data structures. The heap will be small at first. As the program runs and requests more memory via the malloc library API, the OS may get involved and allocate more memory to the process to help satisfy such calls. The OS will also do some other initialization tasks, particularly as related to input-output I/O. For example, in Unix systems, each process by default has three open file descriptors: the standard input, output, and error. These descriptors let programs easily read input from the terminal and print output to the screen. We'll learn more about I/O, file descriptors, and the like in the third part of the book on persistence. By loading the code and stack data into memory, by creating and initializing a stack, and by doing other work as related to I/O setup, the OS has now, finally, set the stage for program execution. It thus has one last task, to start the program running at the entry point, namely main. By jumping to the main routine through a specialized mechanism that we will discuss next chapter, the OS transfers control of the CPU to the newly created process, and thus the program begins its execution. 4.4 Process states. Now that we have some idea what a process is, though we will continue to refine this notion and roughly how it's created, let's talk about the different states a process can be in at a given time. The notion that a process can be in one of these states arose in early computer systems, DV66, V plus 65. In a simplified view, a process can be in one of three states. Running. In the running state, a process is running on a processor. This means it is executing instructions. Ready. In the ready state, a process is ready to run, but for some reason the OS has chosen not to run it at this given moment. Figure 4.2 Process state transitions. which illustrates the three states and the movements between them. Blocked. In the blocked state, a process has performed some kind of operation that makes it not ready to run until some other event takes place. A common example, when a process initiates an I/O request to a disk, it becomes blocked and thus some other process can use the processor. If we were to map these states to a graph, we would arrive at the diagram in figure 4.2. As you can see in the diagram, a process can be moved between the ready and running states at the discretion of the OS. Being moved from ready to running means the process has been scheduled. Being moved from running to ready means the process has been descheduled. Once a process has become blocked, e.g. by initiating an I/O operation, the OS will keep it as such until some event occurs, e.g. I/O completion. At that point, the process moves to the ready state again, and potentially immediately to running again if the OS so decides. Let's look at an example of how two processes might transition through some of these states. First, imagine two processes running, each of which only uses CPU. They do no I/O. In this case, a trace of the state of each process might look like this, figure 4.3. Figure 4.3, tracing process state, CPU only. This illustrates process 0 and process 1. Process 0 runs until time 4, and at which point it terminates, and hands control to process 1. In this next example, the first process issues an I/O after running for some time. At that point, the process is blocked, giving the other process a chance to run. Figure 4.4 shows a trace of this scenario. Figure 4.4, tracing process state, CPU, and I/O, which illustrates two processes running. At time 3, process 0 initiates I/O and becomes blocked, letting process 1 run. When process 1 terminates, control is handed back over to process 0, which has been waiting since time 7 in a ready state, to run and then terminate. More specifically, process 0 initiates an I/O and becomes blocked, waiting for it to complete. Processes become blocked, for example, when reading from a disk or waiting for a packet from a network. The OS recognizes process 0 as not using the CPU and starts running process 1. While process 1 is running, the I/O completes, moving process 0 back to ready. Finally, process 1 finishes, and process 0 runs and then is done. Note that there are many decisions the OS must make, even in this simple example. First, the system had to decide to run process 1, while process 0 issued an I/O. Doing so improves resource utilization by keeping the CPU busy. Second, the system decided not to switch back to process 0 when its I/O completed. It is not clear if this is a good decision or not. What do you think? These types of decisions are made by the OS scheduler, a topic we will discuss a few chapters in the future. 4.5 Data Structures. The OS is a program, and like any program, it has some key data structures that track various relevant pieces of information. To track the state of each process, for example, the OS likely will keep some kind of process list for all processes that are ready, and some additional information to track which process is currently running. The OS must also track in some way blocked processes. When an I/O event completes, the OS should make sure to wake the correct process and ready it to run again. Figure 4.5 shows what type of information an OS needs to track about each process in the x86 kernel. Similar process structures exist in real operating systems such as Linux, Mac, or Windows. Look them up and see how much more complex they are. Figure 4.5, the x86 proc struct, along with enum for proc state, and a struct for the context holding different registers. The register context will hold, for a stopped process, the contents of its registers. When a process is stopped, its registers will be saved to this memory location. By restoring these registers, i.e. placing their values back into the actual physical registers, the OS can resume running the process. We'll learn more about this technique, known as the context switch, in future chapters. You can also see from the figure that there are some other states a process can be in, beyond running, ready, and blocked. Sometimes a system will have an initial state that the process is in, when it is being created. Also, a process could be placed in a final state, where it has exited, but has not yet been cleaned up. In Unix-based systems, this is called a zombie state. This final state can be useful, as it allows other processes, usually the parent that create the process, to examine the return code of the process and see if the just finished process executed successfully. Usually, programs return 0 in Unix-based systems when they have accomplished a task successfully, and non-zero otherwise. When finished, the parent will make one final call, e.g. wait, to wait for the completion of the child. and to also indicate to the OS that it can clean up any relevant data structures that refer to the now extinct process. 4.6 Summary. We have introduced the most basic abstraction of the OS, the process. It is quite simply viewed as a running program. With this conceptual view in mind, we will now move on to the nitty-gritty, the low-level mechanisms needed to implement processes, and the higher-level policies required to schedule them in an intelligent way. By combining mechanisms and policies, we will build up our understanding of how an operating system virtualizes a CPU. We have a footnote from earlier about a zombie state. Yes, the zombie state. Just like real zombies, these zombies are relatively easy to kill. However, different techniques are usually recommended. Aside, key process terms. The process API consists of calls programs can make related to processes. Typically, this includes creation, destruction, and other useful calls. Processes exist in one of many different process states, including running, ready to run, and blocked. Different events, e.g. getting scheduled or descheduled, or waiting for an IO to complete, transition a process from one of these states to the other. A process list contains information about all processes in the system. Each entry is found in what is sometimes called a process control block, PCB, which is really just a structure that contains information about a specific process. References. BH70, the nucleus of a multi-programming system. The paper. CK+08, the XV6 operating system. DV66, programming semantics for multi-programmed computations, another paper. L+75, policy mechanism separation in Hydra, another paper. B+65, structure of the Multics supervisor, another paper.